Hello, I'm Albert Kalustian. Along with Matthew Hasty, Benjamin Hunter, and Jim Stewart, we're Team 34, using machine learning for signal detection and classification. We were approached by General Dynamics to train numerous machine learning architectures to detect and classify data signals amidst varying levels of shaped noise. Our project focused on three types of data signals: OFDM, LTE, and WiMAX modulation types. We were given a collection of 80,000 data samples, though the data was deliberately corrupted to mimic the challenges that come with real-life data samples. Roughly 20% of the data was mislabeled, for example a WiMAX signal being labeled as an OFDM signal, while other data simply held zero information. Using pattern recognition and a number of scripts and algorithms, we were able to relabel the corruptions and dismiss what wasn't useful. Our first attempt involved a multi-layer perceptron architecture, which utilizes logistic regression and a feed-forward network. Basically, this approach makes predictions, is rewarded for correct guesses, and penalized for incorrect guesses. This approach turned out to have our weakest results, as this architecture has a difficult time training with complex data. Now, here's Matt Hasty to talk about our most successful architectures.
Hello, thank you Albert. This is Matt Hasty from Team 34 and I'm going to talk to you very briefly about our convolutional neural net and our long short-term memory network. So if you look at the right screen here, this top figure, it shows a training phase for our convolutional neural net. This was a one-layer CNN and it trained on 61,110 signals 14,310 times. And we were able to optimize it to where it did this in just over 5 minutes. So those 61,100 signals are divided evenly by LTE, OFDM, WiMAX, and shaped noise, each consisting of 15,275 signals. The bottom graph shows our losses as the iterations progressed. And as you can see, the CNN converged to nearly 100%, closer to 100 than to 99. So the next figure we have here shows a long short-term memory network. This was one of our better ones. This isn't the one we ended up using, but this one was only trained on the signals 3,900 times, but took 20 minutes and 9 seconds. Now it was a two-layer network, and that would have added some time. However, from our trials, it appears that this was fairly normal. The network we ended up using that got the best results for long short-term memory took almost 50 minutes to train. And this confusion matrix here is a result of it, and this confusion matrix here is our CNN that we have saved. So you can see it got near 100% accuracy, just a few LTE and OFDM signals misclassified during this classifying phase. And our LSTM actually was very accurate, except when it came to OFDM and LTE being misclassified with each other. Especially this OFDM being misclassified 32% of the time. And of the 15,275 signals, 4,567 of them were predicted to be LTE. That is not good. Anyways, from these two confusion matrices, I have the networks saved to my computer. And I've already preloaded them to save time because it takes 2 to 5 minutes to load them. They're about 1.5 gigs a piece. And I have all the signals loaded, and I'm going to run a loop for examples. So here we're going to start with the selection of an LTE signal. And what this is going to do is it's going to randomly select one of our over 15,000 LTE signals, and it will simultaneously classify it through both my CNN and LSTM networks. And we will, for a visual representation, we will show you the signal itself, which is here. Make it large. And this is an LTE signal. It is a 2 by 1024 array. So the two signals I have labeled as real and imaginary, and they're across 1024 time steps. And the actual signal is LTE, and this is the results of the classification from both the convolutional net and the long short-term memory. So we're going to go through it a couple of times to try to look for an error. There we go. And here we have an LTE signal, and our long short-term memory has misclassified it as noise. Our CNN is still LTE, that's expected. It would be very unexpected if we got one of the about 19 ones that it will misclassify out of this. But if you will just look at the signals themselves for a second, we have LTE, WiMAX, OFDM, and then a shaped noise. I'll go through them faster. And to the naked eye, they're not easily discernible. However, our neural nets are classifying both of these in just a little over 1/10 of a second. And that is the real-world application of this. Getting a trained network that can take a signal that is taken on the fly in the field and immediately tell you what that signal is could be of definite value for our armed forces. And that is all I have for you today, and I hope everyone has a terrific demo day.